How are you, sir?
I'm good. How are you?
Doing good, sir. Doing good so far.
Acha. Okay.
I'll set up some time with you. I have to speak to you for a few things, so I'll look into your calendar maybe, or I'll
Okay.
be WhatsApp you.
Yeah. I'll give you a calendar link, then we can set up.
Yeah.
So ping me on WhatsApp. I'll share with you the calendar link, and then you can schedule. Okay.
Done, sir. Done.
All right. I am busy packing stuff for moving. I hate moving. Man, I think moving is one thing that will force me to buy a house. But the
So,
problem is that, you know,
so you don't have any plan to come to India?
I don't know. I'm thinking of living in Europe for sometime for in US, and maybe sometime in Japan. That's my
No, so India is not in list.
India. I lived in India for 40 years. And yeah, I think I mean I miss everyone uh, from India, but the thing is
But
that
you have office in Bangalore, right?
yeah.
Where these people are sitting?
Most of the
Gargi
people,
and
yeah. So Gargi is in Gurgaon. Uh,
okay.
Rajendra is in Himalayas. Okay.
Ah,
He has been living in Himalayas for more than 6-7 years. He couldn't,
okay.
yeah, he went to Aligarh, his hometown. He didn't like it, so he went back. So,
Hmm.
yeah. And yeah. And one person is in Lucknow, other person is in distributed, everybody. Now the team is growing, and yeah, and there are more things happening.
Hmm.
So I think distributed, I think the physical location doesn't matter.
Right.
As long as you have good space for yourself, you have internet connection and electricity and a good computer, that's more than enough.
That is true. I think after COVID, a lot of things got changed.
Yeah.
Small startup mostly closed and shut down their offices in costly
No, I
city
think,
and
see,
all.
I was online before COVID. I got so I got so sick of going to Amazon office
Yeah.
that when I left Amazon, I had decided that whatever I do, I'm not going to go to office. I mean, it looks very weird. You go to office, carry your own machine and do like office was something like you go and work on a machine, right? Office, the whole idea of office comes from factories, right? Where you go and work there. But and I don't think it makes any more sense. Basically, right? And it's not like you have to. I mean, my entire work is has been always pretty effective with all my teammates. Since 2014, I have not had an office. Since
Oh,
20. Yeah, okay. My teammates, they wanted that, oh, we like to work with you. We wanted to work with you and all that. So they had taken office, and I used to go sometimes, and that's all. But I did not. That too, I took an office in the same building where I live. I used to
okay.
live in Bangalore. So yeah. So I think, yeah, I did not. I had decided not to just go to office. That's all. Okay, just it doesn't make sense. It does not make sense. We we met like I had not met Gargi and all the teammates. I did not, and I never met them in person. So in 2020 January, I had taken up a place in Goa for around 2 months. We met there. Okay, 2020, 4 years back
Hmm.
in Goa. So that's time we all met. And yeah, and I met Gajender in IIT Roorkee campus when he came for the campus immersion. Personally, I did not meet.
So
And
he was your student?
No, Gajendra is not my student.
Okay.
No, I'm saying that most of my teammates, I had not met them personally. I met them like once or twice. My co-founder is Abhinav, was my student. He left this Byju's as from architect position to join me. He is my student.
Okay.
He'll most likely he's just finishing up his MS, and most likely I've asked him to come over to Canada. So I got him the PR, permanent residence, and everything here. So I'm hoping that he'll come. So yeah, and I think it's not necessary. I mean, India as a concept, right? It's just a concept, right? Okay, if you see North India, South India, everything is like so different, and it's just so different. Like the language is different, and yeah, culture is different. Lots of things are different. So I think India as a concept is very abstract and arbitrary. So yeah, but I mean, I feel here in Canada, I have spoken more Hindi than I have spoken in Bangalore. You won't believe this. Yeah. And anyway, good. Let's carry on where we left off. So we were, all right. Perfect. Before we start, do you guys have any questions for me? No questions? Subodh,
No, not for now.
Aman?
No, sir, not now.
No.
Recording in progress.
Sorry, guys. I don't know why doesn't it remember my preferences. Okay, I'm all set. Let's start. And yeah, let me turn off my phone. Yeah, perfect. There we are. Okay, so first thing first, let's start with fresh notebook in this folder. And other than that, we will start with this notebook. Is everybody following what we have discussed so far? No? Yes?
Yes.
Okay. So we basically, we given two data points. If we have to figure out a model, we can only figure out a straight line, right? And we learned how to fit two variables, find out the slope and intercept, and that's it. If you have three variables, we can fit a straight line through them, figure out the parameters for the straight line. And it's not a straight line, it's essentially a plane that we are fitting through three, not plane, it's a plane. Okay, it's essentially plane with 3 dimensions. Okay, 3 dimensions. All right. Now, then we talked about how do you solve this using code. We basically learned to solve the equations using the code. And then essentially we did it in 2 parts. First, we normalized this matrix. We converted it into a upper diagonal matrix. And then we solved it. Okay. And once we solved it, right, then essentially, so solving equations was about first normalize it, like converting it to upper diagonal matrix, whereby it becomes like from bottom equation is left with one variable, then top two variables, then three variables, then four variables, like that. Correct? So essentially, if we, right, if I ask you a simple question that you have x plus y plus z equals to 10 and y minus z equals to 30 and z equals to 2, right? This is z. Okay, so you can simply start from here, z equals to 2, and then put it into this, and then you can calculate y. When you have y and z, you calculate x. That's what we are doing here. So first we converted a complex equation into such that we have these ones, right? So we kept on eliminating. First we eliminated x, then we eliminated y, and so on. Okay, so that's what we have done as part of normalization, and then solving normalization is pretty simple. Okay, so that's what we coded earlier. Then we said that, okay, with the same equation, same strategy, we can also fit a quadratic equation into the data. If you have the data and you know the relationship is not straight line, you can fit a quadratic equation. So we learned how to fit a parabola or a curve through 3 data points. So we said, okay, traffic is some constant, time square plus b. B is another model parameter, so you can say sort of, and that's it. Okay. The other way to look at it is that we took the traffic, we took the time, which is the input parameter. Okay, we took the time and added one more column called time square. Now we have time and time square, and then we fit the plane through it. And that plane is essentially what a parabola is. Okay, so that's about it. Okay, that's about it. So this was a very interesting discovery whereby, you have you're trying to fit the quadratic equation, but you turned it into a multidimensional problem. And this strategy would be followed in multiple models in future. For example, when we introduce kernel or when we solve the polynomial regression, this is the strategy we'll be using. Okay, so we learned how to fit a parabola into the data points. Okay, and we use the same strategy of solving equations. And then basically, right, we see over and over here in all of these that there is always loops and loops and loops again and again, and we have to code so many loops. Okay, and so a common pattern comes out all of these is that vector products and matrix products are something. If we can just create functions for the same, that should be good enough. Similarly, subtracting one vector from another. Essentially, people observe that in lots of mathematical functions, when there are too many equations, you have to keep on adding, subtracting, multiplying vectors again and again. Or vector is nothing but a list of values. So instead of you writing the for loops, you basically create these functions which can do the things for you. Okay, and that's the part which NumPy makes it easier. So NumPy provides something called array, which is nothing but list of numbers. You can do things like dot product of two vectors, subtracting one vector from another, and so. Okay, so that makes our life easier. We don't have to code this much. Okay, now afterwards, after we had fit in, so first 2 variables, then 3 variables, then quadratic equation, and then we started with a linear approximation. If your data, let's say you have 3 data points and you have to fit a line approximately through this data, okay, there's a slight bit of mistake in the data. Then we learned about, how do you fit the line? How do you fit the line? So we first, right, we did the overall approximation, right? We created we assumed the line to be mx plus c, and these m and c is something that you're going to find. Okay, in this equation, x is given, y is given, you have to find m and c. Okay, so we defined like error, like how much error is there. Now our problem is, what will be that m and c values for which error is minimum? Okay, is everybody clear what's going on here till here? So we have 3 data points. These are my data points. Okay, and 1, 8, 2, 11, 316. Let's see. 1, 8, 2, 11, 316, right? So we basically say that when we fit for x equal to 1, y is m times 1 plus c. And actual value is 8, so the error is this much. Then error is this much, then error is this much, due to the 3 data points. So overall error is the total square, and summation of this square is the total error, right?
So Sandeep,
Yes.
why we taking a square here? Because we are using this y is equal to mx plus c, right? This is the equation.
Correct.
But then why we are,
See, individual error is how much? Individual error is mx plus c minus 8. Are you clear about this? The individual error is this much. Now, if we just sum it up normally, right? If we sum it up normally, then basically what will happen? If this is negative, this is positive, they will cancel out, right? Therefore, we don't want the errors to cancel out, correct? The negative error is also error. So either we do the absolute, we can do like my total error is absolute value of this, absolute value of this, and absolute value of this summed up together. So that's also a valid error. Okay. If you square it naturally, right? So let's say if this was your data point, this was your data point, and my line is like this, right? Here, the negative, the error is negative. Here, the error is positive. Okay. Predicted value is bigger than the actual value. Predicted value is lesser than the actual value. So you can see, right? This is, if this is negative and this is positive, they will cancel out. Therefore, either you take the absolute value, you can also take a square of these values, right? And you can also come up with the other, the error function. What was the error function that we discussed? Something between absolute and square. Does anybody remember? No? Huber laws. Okay, you could do Huber laws, absolute value, square. You can also do, say, to the power 4. It's up to you. How much complex do you want to make it? Okay.
So the reason of squaring is just to ensure that we don't miss the positive and negative, right? So negative will also convert it into positive, and then you get some value for the error, right?
Yes. Yes.
Okay.
Okay. So it's up to us what we want to do. Okay. So absolute value essentially kind of tries all of them slowly, doesn't emphasize this too much, but square gives too much emphasis on individual ones. And people realize, like Huber, basically somewhere between absolute and square. When the values are tiny, use absolute. If values are big, use square. That's the idea. Okay. So yeah. So it's up to us. Now, what is simpler for you? Okay. Can you differentiate this equation with respect to M and C? If you have to differentiate E with respect to M, can you do that? You know what is the differentiation of x squared, correct? Right? If it was absolute, for a moment, let's just take a case that we have, let's say, error is equal to absolute value of m plus c minus 8, then 2m plus c minus 11, plus what was the third value? Third value was 3m16, right? Okay, 3m plus c minus 16, right? This is, let's say, our error. How would you calculate rate of change of error with respect to m? You don't know how to do the differentiation of absolute. And also, the absolute is a crazy thing, right? How do you define absolute, right? How do you define absolute? You define absolute like this. If x is less than 0, return minus x. Otherwise, return x. Correct? That's how you define absolute. Okay, so there is a if-else condition. Correct? Now, if you have to differentiate this, it would be like this. If x is less than 0, the differentiation of absolute is how much? Absolute is -1. Otherwise, minus a. Okay, and so on. So it becomes a problem there. Okay, so also please notice that if x is equal to 0, then the absolute value could be negative, could be positive, correct? And therefore it is not continuous. This if-else condition is not really valid when x equal to 0, correct? Therefore, people do not prefer the absolute value usually. Okay. So computing differentiation for the absolute value is hard. That's why we generally go for this. But it's a valid question, right? You can choose any error function that you want. Okay. You can also come up with better loss functions. Okay. You might come up that, hey, this is a wrong way of measuring. You might say that this is my one data point, this is another data point, and right? And you might say, hey, I don't like this idea of fitting the line like this. What I want to do is I want to fit a pipe or lane, a street through this data so that all of these data points are within this lane as much as possible. Now I will try to minimize three things: the width of this street, and all these data points should be within the street. And once I'm done with that, so you can come up with those ideas. So keep your mind open for those ideas. This is not the only thing. Okay, this is a general practice, common practice, and this is chosen. The square is chosen as a uh, convenient mechanism. So it's not really cast in stone. Okay. Probably if you asked me this question few years back, I would have said, no, you have to use only the square, right? Not couple, like if you asked me this 5 years back, I would have told you this. But as I grew, I realized that there are many loss functions for many scenarios. Okay, perfect. Good question. Right? Anything else? Right. So we talked about this one, and when we plotted this graph, the axis square kind of graph, this looks like this, which means there's a value for which a minima existing, and there's only one minima. Okay, rest is all bigger. Now, then we talked about the differentiation. We said that differentiation is nothing but rate of change. Okay, if x is your distance, differentiation is speed is first derivative of x with respect to time, how the distance is changing with respect to time. Rate of increase of distance per increase in time. Okay, acceleration is rate of change of speed. It's not really rate of change of speed, it's essentially rate of increase of the differentiation is not really rate of change. Okay, it's rate of increase. Okay, because if it's not increasing, we'll say that it's minus sign. Okay, so rate of change is it's not like absolute value. Okay, so it's essentially rate of increase. All right. You can think of this delta d as delta. Okay, so it's only the symbols that are confusing. Otherwise, pretty simple. Dx by dt is distance 2 minus distance 1. Moving on, the other way of looking at a function is you have input x, you are getting y. If you increase x, what's the impact on y? Okay, then we talked about the various differentiation. So we figured out that one of the biggest use case of differentiation is that if we calculate the gradient and the derivative, differentiation, and gradient all are same thing. Okay, all are same thing. And one of the most important use case is to do the like minima, maxima kind of problems. Okay, it's used a lot. And we talked about like the derivative of constant is 0, right? And then derivative of, let's say, a linear value is 1. If you multiply constant to it, the answer is constant times that. Okay, the differentiation of square is 2x. Okay, twice of that value. Then differentiation, right? Then basically this is just now we said, if you basically say a times something, then the answer is a. Okay, now then we talked about a chain rule. Okay, a chain rule. Chain rule means that if you can express something like this, okay, let's say you have y equal to this, you can say z is equal to 3x plus 2. So y has become y is equal to z square. We know z is equal to this, and so on. Okay, and now here when you differentiate dy by dz, which is basically this dy by dz, times dz by, I'll just correct it, okay? So partial derivative of y, okay, d, okay, dz, okay. So dy by dx is same as dy by dz times dz by dx, the chain rule, right? So it becomes, okay, 2z, okay, and 2z times, what happened here? So we are saying 2z, dy by dz is 2z, and then the differentiation of this one is 3, correct? So we can, this is going to be like this, right? So 2z times 3, and that becomes, right, 2 times 3x plus 2, that's what is z, and there is 3. Okay. Okay. This will be how much? 18, right? That's okay, right? Are you guys clear about it? Okay. Now, okay. Now, again, we talked about like what happens when you have two functions like this, a into b. So that you can, by using first principle, you can actually derive this. first value times differentiation of second plus second into differentiation of first. You can actually derive this. Okay. Are you guys okay?
Yes.
So whatever, let's say you have a function like this, okay? Y equal to x square times x square, okay? And you have to calculate dy by dx. So what you do, this value as is times differentiation of this value plus this value as is times differentiation of this one. And it will be how much? It would be 2x square this, so which will become 4x cubed, correct? So you can essentially derive many things like this. Okay. Are you guys okay?
Yes.
Okay. All right. Now, yeah. Good. Let's move on and okay. In case you have to prove y equals x to the power n, and we can write it like x to the power n minus 1 times x, right? Now you have to do dy by dx, which turns out to be differentiation of the first one, x minus 1, right, by dx times 1 plus x times x to the power n minus 1. Okay. Right. So when you do it recursively, you will be able to note that this term is getting added over and over n times. Okay. No, I think this is x and this is 1. Okay. This is x times this and this is 1. Okay. And yeah. So you will find that in the end, right, if you keep on going like this, okay, right, if somebody wants you to prove that, right, this formula, remember, y equals to x to the power n, dy by dx is equal to n times x to the power n, right? This is the formula that we had studied, right? If you have to derive it, in how many ways can you derive it? Okay, first way is that we say y equals to x times x minus 1, and then we can say dy by dx is equal to first value, the derivative of the second value plus the second value and derivative of the first value, which is 1. Okay, so the differentiation of x to the power n is this. Okay, x to the power n minus 1 plus x times, right, the derivative of x to the power 1. Okay, now the derivative of x to the power n minus 1 will be in the same way. You will again say x into x to the power n minus 2. Okay, and right, so it would be x and minus 1 dash plus x to the power n minus 2. Okay, like that. Is it correct? Right? Now, if you put this value back here, what it turns out to be x times x, x times x to the power n minus 2's differentiation. This dash represents differentiation. plus x to the power n minus 2 plus x to the power n minus 1. And when you multiply this, it turns out that it became x square times x to the power n minus 2's differentiation plus twice of x to the power n minus 1. So if you keep on doing it over and over, this will become, the answer will turn out to be n times x to the power n minus 1. Okay, because every time the term is adding up. Okay, so with first principle, you can essentially, derive all the things that you had memorized in case of differentiation. Okay, all the formulas you can derive. Okay, so I do not want you guys to just memorize all the formulas blindly, but know how to derive those. Okay, because there are many use cases of differentiation, right? Like you might have to differentiate a function, you might have to differentiate an image, right? So like, for example, given an image, given a photo of a person, if you have to find out the edges, right? Where are the edges? What will you do? How would you compute it? So one of the strategy is compute the rate of change of pixels, right? In an image, okay? Meaning the first derivative of the image with respect to the width and height. Okay, so you basically compute the first derivative of the image. Now that is very weird because we never thought of differentiating an image, right? We always thought of differentiation is always a y equal to x square. We never thought that we can differentiate a piece of code. We can write the first derivative of a piece of code, but we do it day in, day out. That is the ground on which the entire neural network stands as of today. Okay, so I want everybody to be like doing the first principles, because I know for sure that the impression that we carry for differentiation is very different. The impression we have is it's only possible to compute the differentiation of only the known function, but you can't compute the differentiation for unknown functions. A better way to look at it is just a rate of change. You increase the input a little bit and then observe the rate of increase in the output. And the ratio of the two is essentially the first derivative. Okay, so think of it that way. Think of it that way always. It's just a rate of increase. Okay, if you notice closely here, so I talked about the minima maxima earlier, and what we did was we observed that the first derivative is 0 at minima or maxima. Okay, first derivative is 0 at minima or maxima. So what we have to do, we basically have to differentiate E with respect to M, with respect to C, equate them to 0, compute M and C, and that's about it. Okay, we got two equations to solve, and so if there are 100 columns in the data, there will be 101 such equations, and irrespective of how many rows of data is given to you, if there are 100 columns, there will be 100 equations. Okay, if there are 1,000 columns in the data, there will be 1,000 equations. Okay, and 1,001 equation. Okay, and solving equations is a tedious task. For solving n number of equations, okay, the complexity is O n cube. If you have n number of features, your complexity is O n cube. Therefore, if there were 1,000 features, it will take 10 to the power 1,000 to the power 3, 10 to the power 9 permutations. Okay, so not permutations, 10 to the power 9 iterations. Okay, so this strategy might look straightforward, but it is fairly intensive as the number of columns increase. Right, so yeah, we did all of this using our strategy. Now we figured out the value of this. Now, cool part about this is that if you solve the equations, there is no need of a hyperparameter tuning. Okay, hyperparameter tuning meaning you don't have to iterate, you don't have to worry about when to stop, when not to stop, and so on. You just basically solve the equation, you get the answer. End of the story. Okay. Now, there are lots of downsides of this approach. Some things are better. There are nothing to, hit and trial. It's just straightforward solving the equation. But if your loss function was to the power 4 here, okay? If loss function had, instead of square, it was to the power 4, we'll get the equation, cubic equations that we can't solve that easily the way we solve these linear equations, right? And therefore, this strategy does not work out. Okay. Similarly, if somebody comes up with some other, like a complex function, like let's say somebody say, I would compute the log of this value, multiply the log of second value, and that will represent my loss. Okay. Now, solving those differentiation is going to be hard. Okay, right? If somebody like if y equal to x log x, what happens to dy by dx is it becomes log of x plus 1, right? And then solving this equation equal to 0 and solving this equation is going to be fairly hard. Okay, so usually the square, there's a reason, another reason of choosing a square is to be, because these equations are easier to solve. And as you differentiate these equations, become linear, it's easier to solve, right? So this strategy is good. We call this a normal equation or sum of least squares. But this is not really great because it doesn't scale well when the number of features increase or our loss function increases and loss function becomes complex. This one doesn't work out well. Now, the next thing we discussed was the using the gradient descent approach. Gradient descent approach is called greedy optimization. Okay, instead of trying to find the best possible solution, what we do is we just try to guess, just a little intelligent guess, rather than jumping to every place and trying all the possible values of M and C. We basically just go a little clever. Okay, we see which way seems to be my minima and I start moving to that direction. That's all. Okay, and we just observe which way it seems to be minima and we basically move to that direction. Now, how much to move and what should be our size of step and so on is all debatable. Okay, and there are different variations of gradient descent approach. Different variations like Adam, Nedam, the what do you call that, momentum. So there are so many new variations coming up for the gradient approach. Okay, then we learned how to differentiate a function. Here we wrote a function f and x. We basically computed the rate of change and returned the ratio. Then we proved that it actually works. And then afterwards, we made it simpler by using the NumPy. Okay, instead of playing around with arrays, we just did that. But in this class, I had done everything using normal arrays rather than NumPy. Okay, then what we did was we basically generated data and then we essentially solved it. Okay, so that's all we have done in the class. Okay, we have also, because we did the gradient descent first and then the least squares one later. Is everybody on the same page so far? I did a recap in last 45 minutes. Okay. Yes, no.
Yes, Deep.
Have I put you to sleep?
No, good. I mean, again, differentiation was not one of my favorite subjects, but we understand that. But again, gradient descent as we go ahead, having understanding different forms of the gradient descent will be interesting. So looking
Yeah.
forward for that.
Yeah. Always, right? Always resort to an optimized, like the first principle way. Don't memorize anything. Okay, that's my request to all. It's easier, convenient, and tempting to memorize. And yes, and of course, every learning starts with memorization, and then we regularize. Okay, even in our case, in case of this class, it's okay to memorize sometimes, but learn to forget as well. Learn to question that memory. And so every learning starts with memorization, but you have to regularize it. You have to forget parts of it. And as you basically break down a big brick of memorization into smaller and smaller and smaller, you will do pretty well. Okay. All right, moving ahead. So we learned about this. Now is the time to move on to our usual class. Where is my usual?
So is gradient descent good for fitting polynomials? Because the last time we had done it, uh, it was giving a lot of error. Like it was not as accurate as um, the linear predictions.
Which one? Gradient descent.
Yeah.
Oh, it's good. It does all the job. You basically just have to either make it go little fast or little slow, or you just have to, learn to drive it.
Okay. Like I was trying to do the code for the polynomial, and I don't know, somehow gradient was 0 and the error was not changing even though I tried
Okay.
change
Yeah, show me the code.
eta.
Okay. Let's solve it. I think this is a good exercise. If anybody else tried and it's not working, now is the time to try it. Okay. It's important because this is exact, when you finish entire machine learning and your model is not training, and that time you will say that, oh, this is the same problem that I faced when I coded my own gradient descent. Okay. And yes, so I think this learning is inverted, but this is the right way to done. I can guarantee that part. Okay, let's just debug it. Do you have that notebook now? If anybody tried and failed, now would be the time to debug it. Okay. All right, let's see. Let's take a look. It's for everyone. Could you zoom a little bit? Yes, thank you. Okay. Oh, it did not reflow. Anyway, just zoom it back to 0. Control. You're on Mac or Windows? Okay.
It looks Windows.
Windows, okay. You can say Control plus or something. Never mind. Let's start. So differentiation. So you have the loss function, you have weights, and you are differentiating this loss function with the weight at index position. So what you did was you made a copy of the weights, okay? And then you increased the value at index with D. Oh, your D is too high. Your D is too high. Just change the D to 0.00000001.
I tried doing that too. Like it was 0.0001.
Just
Uh,
do it now.
okay.
Yeah.
Okay.
Okay. Otherwise, it'll just keep on jumping back and forth. Okay. Now let's see. Is the now when we are saying this perfect? No. You have to, before increasing, you have to compute the value as well. One is after increasing and one is before increasing. But GG will be 0 here. You see that? GG will be 0. So just before you increased the ith value, we have to calculate like previous value and second value, correct? So yeah, you see that?
But I'm directly
Okay, how
calculating
much
the
is y2? How much is y2?
y2 where?
See, loss function of weight 2 and loss function of weights is same thing, because what happened was you made a copy and you increased. Okay?
Yeah.
Wait. You are right. You are right. So weight 2 is this. Okay, perfectly fine. Weights is you are making a copy. Perfectly fine. You're right. You're right. Okay. And then you're dividing it. Okay. Yeah, this seems okay to me. Is it okay, Ranveer? This differentiation function? No, it looks okay to me. Okay. Now, what you're doing here is you're saying for epoch in range 1000. Okay. And okay, at every 300th epoch, you are increasing eta. Okay. You can comment out that part. We'll just test it out. Those first, yeah. This is this is called learning rate scheduling. Yeah, thank you. So epoch, current loss, squared loss of this. Can you show me the squared loss function?
Oh,
Squared loss, this is weight, and what you're doing is for I in this predicted value, y predicted is weights 0. Is that right?
yeah, I checked it from the original code that you had done in the class.
So
No, why should we wait 0? Why predicted should be
okay. Y predicted should be weight 0. Yes. And then you have to increase y predicted plus equal to. Yes, there it has to be plus equal to. Yes. Okay. So you are saying enumerate. Okay. One more thing. Yeah, this should be good. This should be good. So 0th value, you put it in y predicted. Then for 1, 2, 3, you're doing this. Perfect. Okay, let's see. And yeah, weights will be 1 more than the x, correct? Weights will be 1 more than the x. Okay. Uh, okay, this is perfect. Now that's your total error. And y predicted is this yi minus. Okay. Okay, this is good. Is everybody okay with the squared loss function? To me, it looks okay. Differentiation looks okay to me. Now, let's go down to the epoch. Observe that. So we are saying, first of all, okay, for I in the range. Okay. Okay. We calculate the gradients. Yes. And then we are applying the gradients on every weight. Perfect. This is okay.
Should I run it?
Yeah, you should run it. Okay. Weights is not defined. Where?
I'll have on.
Oh, did you initialize those weights? I did not see them initialized.
Here, this one.
Where?
Yeah.
Oh, you are appending right now. Perfect. And you did the one more than that, right? One more than the length of x.
Yeah.
Wait. Can you go up? Can you go up? Can you go up?
Oh,
Yeah, it's bouncing a lot. Okay, can you go up? Yeah, I want to see where have you initialized the weights? Yeah, weights is this for I in the range of one more than the length. Perfect. This is all good. Yeah. Okay. All right. Now let's take a look at the first iteration first. Okay. Looks like the value, the law. Yeah. Let's look at the 0th one. It's jumping a lot. Can you reduce the learning rate? Just, yeah, let's test it again. Start with the zero, reinitializing the value again. Reinitialize the value of weights. Okay. It's going down, but it's going down. Is it going up or down?
it is going down, but it's very slow.
Slow. Okay. All right. Now let's take a look at your eta times GI. Those are weights. And how are you applying these weights?
Sandeep, in SQL loss, right? That y predicted we are increasing actually. It should not increase because
wait. So what he did, what she has done, Nikita has done, what she did, ith weight equals to old weight minus eta times the gradient. Okay. Looks okay to me. And okay. Differentiate. Looks okay to me. Yeah. Now come back. Come again. You were saying something. Sorry to not focus on what you said.
in SQL loss function, right? Dear?
Yes.
So y prediction we are increasing actually. It should not supposed to increase. This y predicted because we are calculating total error, right? There we are just
Oh, no. So y predicted is this. Okay. What we are doing is y predicted. Okay. Y predicted is equal to W0, W1x plus W2, W2 x2 plus W3 x3. That's what doing. So W0 is this, W1 is this times x of j, and basically she's computing y predicted here in this loop from here to here. Okay, got it. And then once he's completed this one, subtracting this, okay, and then squaring it, and then adding to the total error. This is the total error. Do one thing, reduce the value of D. One is reduce the value of D, okay, and yeah, change the, and then we will do the other one. Okay, let's do this way. Okay, just put more zeros there, more zeros. Yeah. Now observe. Initialize also. Yeah. Okay. It is dropping but slow. Now let's try to increase the learning rate. Just change it to 0.002. Yeah, let it be this way. Let's just see, observe. Yeah. No, it's bouncing. It's bouncing. It's bouncing. So reduce that again. Just make it like 002. 002. Yeah. 2. Yeah. Let's see. Can you reinitialize the weights? Okay. Okay, come down. Okay, come down. Come down. Yeah. Now let's take a look at your data. Is your data, I think it is reaching the saturation somewhere down. Okay. And let's take a look at the data. Where did you get this data from?
The original one.
Oh no, okay, yeah, the training data.
This one I predicted.
Okay. So you are saying x1 square. Okay. X1 square and x2 this plus some random. Can you remove the first x1? Just x1 square instead. Yeah, make it x1 simply. Let's observe. Okay, let's observe this. Okay. We'll come back to this again. I think it has reached the saturation. No, it can't reach saturation so quickly. Go up. Go up. Okay, so your current loss was 8 million, then it reduced, then it reduced, then it reduced, it kept on reducing. Come down, come down. Yeah, it kept on reducing, it kept on reducing. And then I think this is where it has settled down. So 155 times x1. Okay. 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 Can you go up? Let's see. I think the noise is just too much in this. Okay. 5 times random plus 5 times random plus 67. Okay. Okay. Yeah. Can you run entire thing again from the top to the bottom? To me, everything looks okay. Everyone, please help. Okay. Okay. So it says 152 times x1, 47, 222, and 102. What are these values?
These are weights W0, W1.
Okay. Okay. And all right. Can I take a look at again the x, right? 1, 2, 3, 4, 4 values. Okay, go up. Can you go up? Yeah. I just want to understand it. X1, X2. Oh. You okay, so you can just took some random value x1 and x2. Okay, that becomes your input variable. Y is equal to 100 times x1 and 300 times x2 and plus 67. So we have got x equals this x1 dot. Okay. Okay, you are also adding more columns, x1 square, x2 square, and x1, x2. Okay. 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 Now I get it. Now I get it. Okay. If you don't append it, let's say new x, and we just want to experiment with normal x, right? Just say new x equal to capital X, then see how it goes. Yeah, just comment out next 3 lines, these 3 lines, yeah. Not this, exclude the weight column. Yeah, and just say equals to capital X. Yeah, I just want to see if it is working for linear. Okay, this one seems to be okay. 65, 107, 302. Yeah, this seems to be okay, right?
Yeah.
All right. Now, what I would say is that now, basically, after this, once you are done with it, then let's take a look at a little bit more bigger values. Okay. So in our this is our given data set. We can try. Yeah, we can try to generate a little bit more meaningful data, and that's, but this is perfectly okay. This is perfectly okay. I think this much loss is going to be there. Okay, just see if it goes down, it goes down. Yeah. Yeah, it has gone, you can see that it is going down, and after a while it has settled down. 65, 100, 300, right? That those are the 3 things that it has figured out. And if you go up, right? 3 to the, like, let's take a look at your equation. 300, 100, and 65, 67. So it has figured out correctly, right? Instead of 67, it has figured out 65. Instead of, 100, it has figured out 102, and instead of 300. Yeah, so this logic is correct. I think now you try making the data complex slowly, and then observe how it goes. Okay, good, wonderful, great job. Okay, I hope everybody is clear what changes we made. One was reducing that delta value, and other was that plus was missing. That's all. Okay, very good, very good. And these are the real challenges, by the way, everyone. When you are going to do it using, let's say, what do you call that thing? TensorFlow, for example. Okay, and you realize that it's not working out well. Okay, then what do you do? Now, what you can try, Nikita, is that instead of Huber loss, you code, sorry, instead of squared loss, you code your Huber loss. Observe how it's going, right? So, and there you'll be able to figure it out. Wonderful. This is a very good exercise. I think everybody must do it. Okay. Try, instead of
Yes.
squared loss, try absolute loss, ABS loss. Observe how well it goes. Okay.
Should I stop sharing?
Yeah. All right. Wonderful. Wonderful. Very good job. Okay. Anybody else tried and failed? Okay. Veena, Subodh, Pratik, Rahul, Ramnik, Rupam, Anish, Shweta, Siddharth, Somasri, Suneet.
I just tried whatever we have done in the class only. I have not
Okay.
tried problems.
Oh,
I'll try with Huberlos.
Gradient descent worked?
Yes. Yes.
Oh, wonderful. Wonderful. Okay.
Deep in gradient descent, it is to the one equation may have multiple solutions, let's say multiple minimas or multiple maximas.
Yeah.
So is there a practical way to go towards a global minima or global maximum?
Correct. Very good question. Very good point. So there is no great practical way, single practical way to have the multiple minima or maximum. Okay. The thing is, the problem is if you have like multiple minima or maxima, okay, then what people usually do is they kind of what they do is they basically iterate over the whole data set. Okay, if you calculate your loss using the whole data set, the chances are that you will go towards the global minima. Okay, if you just pick, say, 2 examples and test, right, the gradient descent, those 2 data points could be somewhere on the curve and then somewhere near some local minima, and then you might end up there. So it's generally advisable to have more than one instance on which you evaluate your loss function. Okay, don't just evaluate on one data point or 2 data point. So the other important thing to keep in mind is that when would you have that multiple minima or maxima, right? When your loss function is non-quadratic, okay, if your loss function is to the power 4, there would be like if your loss function is linear, or whenever you are computing the gradient or computing a plot, right? So if your equation is, okay, let's take a look at this. Okay, let me share my screen, what I need to say. Okay, so if your loss function is quadratic, right? Y equals x minus x0 square. Okay, so this is a quadratic equation between y and x. Okay, in my case, it will be m, right? So since it's quadratic, the relationship between y and, right? Remember y equals to let's say 3m plus c minus 10 whole square, right? Like that. And we have more such values, correct? So this is a quadratic equation, correct? And how many solutions will it have? It will have, right? The value of y is going to be 0 or minimum at only one point, okay? It will basically have only one minima, okay? But if it is cube, the equation might be like this, meaning there will be one maxima, there could be one minima, right? And if it is to the power 4, it could have 3, okay? So since we are going with a simpler loss function, the minima or maxima would be only 1, okay? So like, for example, y equals to, let's say, x square minus 10, right? So you can see that there is only one minimum, correct? Right, so you can see very clearly that there is only one minimum. Now, if it was a cube, okay, right? So you can see clearly here that How do I? Yeah, now you can see this. I'm also, experimenting with the equation. Where did it go, man? Never mind. Okay, this is, it's giving us. How do you center it? Yeah, somewhere here. I just now came up with good solution, but then it went crazy. Yeah, this is good enough. Yeah, you can see it has two minima, one maxima, other minima. In case of a cube, okay. And in case of to the power 4, you will see more, more. Okay, so you will start observing that there are more. So there is one minima here. I mean, that's a kind of a theory that you will see. Okay. Okay. Anyway. Should be good, right? This should. Yeah. In case of to the power 5 also, you will usually have like 4 kind of solutions. All right, never mind. So I hope you got the picture. If you have like more complex loss functions, the curve that you're fitting in could be basically really complex. Okay. And okay, so I hope that answers your question. Okay. In case you guys lost the context was what happens when you have multiple minima and maxima. First is that if you are trying to fit in the data into this loss function, you have a loss function which is squared. You will have usually basically one minima. Okay. That's another reason why we want to keep the loss function simpler as a squared loss. Okay, everyone. All right. So I hope that was clear.
Sandeep, one question. So if the loss function is complex, then the gradient descent will not work as good as it is working.
Yeah, there would be multiple. It might get stuck in the local minimas, right? If you, let's say your curve is like this. Okay. Now, let's say first random guess is this. This is the value of M and C. This is somewhere in the curve. This is the value of M it has found. Now, it observes that the rate of the gradient is pointing to this side. Okay, so it will slowly go to this side. Then here, then you just wait there and sleep and not basically, go anywhere. Okay, and just settle down here. So to disturb this process, usually what people do is they kind of let you just choose a random data point. Say if you are taking this value here and you are computing the loss, right? Let's say here, one here, other here, another here. So the chances are that you will basically get out of the local minima. Okay, and otherwise you'll just settle down here and that's it. Okay, just settle down there and that's it. Now, to avoid that, people use stochastic gradient in the sense that they'll pick a random instance somewhere, go somewhere, and then do again. Now, that's the thing. Okay.
There will be multiple random guesses, and we'll do the gradient descent multiple times. Is that the same? It's a variation of gradient descent.
Yeah. You basically randomly pick a single point and then jump out of it. Otherwise, you'll just get stuck there. Okay. So when you have multiple kind of minimas, that's where it becomes kind of, I mean, that's a problem with almost every algorithm. Okay. If it's a complex equation, you can't solve it using normal system, using even the normal equation. Okay. Normal equation will not even work. If it's not mean squared error, you can't really compute the gradient. Even if you compute the gradient, solving the cubic equation is going to be really hard. And cubic equation will lead to multiple solutions of M and C, meaning multiple minima or maximas. Okay. Yep. So I hope that answers your question. Cool. Everybody okay so far? All right. Did we discuss this? No, NumPy. All right. So let's start with our NumPy. Have we discussed NumPy so far? No.
No.
No,
Okay.
not in detail. We just referred it a couple of times, not in detail.
Okay. All right. Let's start with the NumPy then. Okay. And yeah. So NumPy is nothing but a nice array, which is fast and which provides a lot of functions, right? It's a package called NumPy. So I'm saying import NumPy as NP. And then it provides a lot of functions. You can see there are all kinds of function, absolute, right? ABS is absolute is separate function. And then you have all minima, maxima, any value, and so on. It provides hundreds of things. Okay. And you can always just say dir np. That shows everything to you. And you can say at any point of time, you can say np dot, let's say help np. Okay. All right. Oh, you can't do this. If you want to find out the definition of a particular function, you can say this. You can say, you can basically just say this. So it's what? Did we not? What's going on here? Okay. Yeah, I think this is better. It shows calculate the absolute value of the element wise. Now here's a powerful way to, one is if you have a normal array, you can just say np.array and 1, 2, 3, 4. That's all. So you can see that this is the NumPy array generated. Okay, let's say this is my npx, right? So now take a look at this npx. If you say times 5, okay, if you say npx times 10, every value is getting multiplied with this. If you say n, right, plus 4, all the values are multiplied with 10 and then added with 4. You can see that? Now, right, the entire logic that we coded in of gradient descent, we can translate all of that logic into NumPy very simply. It's pretty simple. You can just say things like, okay, I want a bunch of random numbers. So I can say np.random and give me, let's say 100 rows and not 100 rows, let's say 10 rows, 3 columns. Okay, so you can just say np, what? Like this. Okay, let's see. All right. Okay, so it just generated 10 rows and 3 columns. Good. So simple, right? So you can just generate a lot of data. And then let's say, in my case, let's say we want to generate x1. Okay, I want to say, okay, generate one value. This is my x generated. And I'm saying multiplied with 30. And then add it with, let's say, again, slight random number. I'll just call it x. Okay, this is my x. Okay, and let's say y is equal to, okay, x times 100 plus 200 plus, I'm saying np.random 10, 1, right? So what I'm trying to do here is that I am generating my data, right? So I just generated my x and y. Okay, this is my x and this is my y. Okay, and using import from Matplotlib, import plot as plt, and I can just plot my data. Okay, so you can see this is the data I have just generated. Okay, I can just try to make it a little bit more random. Now you can see I just generated my data. Okay, if I want to generate, let's say 100 rows and 100 this, I can simply say this, right? I can also, okay, let's say I want to generate, let's say 1,000 data points, and we call that mm means number of examples, and n is like 2 are my columns. So I can just simply say m comma n, and then okay, I am saying okay, also yeah, I'm just saying here m, yeah, this is good enough. Okay. I don't want this to be like this. Okay, let's just say it like this. Okay, I'm saying give me, so I generated here this data point with n cross n matrix. Now out of this, I'm saying 0th one, I'm multiplying by 10. And then first one, multiplying by 20. And then I am adding with, some random number, let's say this way. Okay, that's about it. Now, right? So I can generate the data really quickly like this. Okay. And here I can say, I have to say like this. All rows, but first column. Okay. What did I do? Where did I go wrong? Okay. So I can also say here that give me all rows, but first column. Okay. Or I can just translate it. Okay, what's going on? Okay, let's see. I think I just moved too fast. Okay. This is my 0th row. If I want to say yes. Wow. It's going on. I'll reduce it to 10 just to play around. Yes. Okay. So yeah.
Sandeep, I didn't follow.
Okay, never mind. Okay, never mind. I think I'm just skipping too fast. Okay, let's just start in a simple manner. So we can define a NumPy array simply like this. You can just convert a normal array into a NumPy array. Okay, then you can basically NumPy array, if you multiply by a number, all of the numbers in the array gets multiplied with that, and you can add values to it. So similar thing I tried to do here. Okay, I said, okay, generate only one column, and that's about it. And I was just doing very simple thing here. Okay, that's all. All right. So I was able to generate that data. I think this is good enough for now. Yeah. So what I was trying to show you is that if I have to quickly do like the way we generated the data earlier, instead of writing for loops, we could do this kind of thing. We could ask NumPy for a matrix of numbers. Here we are saying, give me m rows, one column, random numbers. So x is random. We multiply with 10. So all the numbers in this gets multiplied with 10. We add it with 20. So all numbers are added with 20. And then we basically do the right, add this. Okay. So all the rows are getting added with this random number. Once we have that, then we can plot it. So this is how we just generated 10 records using y equal to mx plus c. Right? Is everybody okay now? Is this okay? Is this clear? So this is how your x looks like. This is how your y looks like. Okay. And then we can plot it. Got it? So 10 times of x plus 20 times this. Okay, so you can see 10 times of x is 8.9. 8.9 plus 20 is 28.9, and then some more randomness. You see that? Then this times 10, which is going to be 1.44. 1.44 plus 20 is 21.44, then some random number. Okay, so I just generated the data. And this is how I'm going to do. Okay, is everybody okay now? Now we know. Does it make sense?
In the gradient descent that we followed, there we used to give like some value into random minus that same value into random, so that it will cancel each other and we'll get the sum like mx plus cs like that, right? Here we are just creating a random.
You can do that. You can do that also, yeah. Okay, like this. Okay, this is what we did, right, earlier?
Yeah.
Yeah, this way, right? I'll just do 2 times 2. So it could be negative or positive, that's all. Now it makes sense, right? Some values went up, some values went down.
Yeah.
Okay. Everybody okay now? Now, moving on. So we just generated the data, right? NP gives you the methods like arange. It generates the data. If you use np.arange and you say 0, 3, and you say 0.1 is the increment, so it will generate all the values from 0 up to, but not including 3. Then we are saying np.linear space, meaning divide 0 to 3 into 10 equal parts. Okay, right? That means that you are dividing 3 by 9, which is 0.33. So 1, 2, so total, how many points will be there? There will be 11 points. There will be total 10 points, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So yeah. So he divided the linear space linearly, the space between 0 and 3 by 9, right? Basically, the gap is 9. Okay. The total points are 10. Everybody okay with linear space? So difference between arange and linear space is clear. Arange generates the data from 0 to 3 with the increment of this. Here, you just give the endpoints and let it fill with the linear space. Okay. Okay. How many data points will it generate, this one? Three by 0.1, right? So total it would be around 30, correct?
Yes.
And this one will generate total 10 points.
It's including 3, right? Yeah, lens space includes and arange includes.
Yeah. Arange is basically going from 0, 0.1, 0.2, 0.3, like that at jump. So it's kind of a for loop in which you are increasing the value until we reach 3. This is first calculates how much increment do we want to give based on 10 points. So it computes what will be the increment. Increment will be this minus this divided by, right? So it'll be, the increment will be equal to, how much will this be? 3 minus 0 divided by 10 minus 1, correct? So because it wants 0 and 3, how many numbers should be there in between? Basically 1, 2, so 8 more numbers to be fit. And how many will be the gaps? 9 gaps, right? 9 gaps. And how much will that gap be? That gap will be this much. So 3 minus 0 divided by 9 gaps. Okay. So that's what it has calculated. Okay. Okay. Now, yeah, you can. Okay. The here you can also use the seed np.random.seed. So if you're using np, use this seed. Okay. When you're using np, use this seed. Okay. And yeah. So this we just now showed you that if you have like experience and right, and you're generating, let's say, this data. You generated experience equal to np.range 0 to 3. Now you can say experience times 15 plus 67, then random numbers. Okay, that should be good enough. So this will generate 30.
Random seed, Sandeep, what is this seed? We used np.random.random earlier, right? What is
Yeah,
seed?
seed basically fixes the values. I'll just show you. So if you basically have like this, okay? Okay, I am asking it to print 5 random values, okay? 5 random values, okay? So random seed. So every time, just after setting the seed, if I call this function, every time the values are going to be same. Okay, so if I just copy paste it elsewhere and then run it again, I'll get the same values. Got it?
And what is the value inside the seed?
It is just anything. It could be anything. You can have like your own secret value. I like 7, so I'll just keep 7. It's up to you. Why? Because when you are experimenting, you want to fix the randomness. Because in case you get to some point, right? Because every time if you are building a model and your initial values of M and C is random, what happens is if things go haywire, you won't be able to reproduce the results, correct? So it's better to just fix the value of M and C, and then once you are all sorted, all the things, you can always just set the seed to something else. Okay, seed is to make sure that the randomness is fixed. Okay, those are basically, that's the main criteria. Like for example, all the values generated after this point are going to be same. Okay, so now you can see, okay, I'll just do comma here. Okay, so you can see here, all the values in that sequence are going to be identical, 0.076, 0.77. You can see this list and this list is same. You can also, if you have the notebook open, you yourself can also generate the same number if you set the seed to that. Okay. Let me see if Google Colab also generate the same.
Sorry, so you're saying that if we use the seed, irrespective to where and how we are doing it, even if the Python version is different, it will generate the same numbers?
It should, yes.
Oh,
But,
that's awesome.
yeah. Okay. It should generate sometimes because of different versions of NumPy. It might have the different ones, but I'm not sure. Okay, 0.076. Is this right? Where is my NumPy? Yeah, you can see. And all this sequence of numbers are going to be same. Okay. 799.38. This almost same. Yeah.
Hey Sandeep, then what is the use of the random here? If the number is fixed, then what was the use of the random?
No, so see, the thing is, it's up to you. You can always comment it out. Okay?
Is
And
it
then
is it
it becomes
is
completely
it
random. Okay.
so is that why it is called as pseudo random? Because it's basically not random, right? If we can
Yeah,
fix it
yeah.
to see.
Yeah. Internally, it uses the seed as the nanoseconds now. Okay, the time. And every time, like, they'll be different. Okay. So basically, what is the use of this? Use is like this. Say you were working on this thing. Okay, and you come back to me and say, hey, it worked, and everything is going haywire, right? Everything is going good, let's say for you. You say, you come back to me, and then when you run it, it's not working. So just to make sure, or let's say Subodh is stuck in some error. Like when he did it, he faced a big challenge. The gradient is not really moving, it's going upwards. And the next time when he did it, it went upwards. Okay. So now he doesn't know what particular thing has gone wrong. So usually you fix the randomness in your notebook just to make sure that the results are reproducible. Got it? Results are reproducible. That's the most important part. That if something is not working, you can rerun it and then test if you have fixed it or not. Okay. Like you basically, let's say your curve is little having like this kind of a minima. Okay. Local minimum. First value of M and C you chose here. Okay. And then you started running the loop, the gradient descent, it reached here. Okay, now you said, okay, let me show it to Sandeep. And then you call me up in the meeting. And then this time when you run it, this time it chose the next value of MNC randomly to be here. And this time it came down and you're happy. You are very unhappy because you're not able to reproduce the result. Okay, so it's better to just freeze the seed. And you have to do it once in the beginning. That's all. Okay, and everything. So like first value will be this. Now when it prints first value, this value becomes the seed for the next value, and the next value becomes seed for the next value, the next value becomes seed for the next value, and like that it keeps on doing that. Okay, so essentially that's how it is. So there is a random seed, the random seed phenomenon. If you don't set the random seed, that's by default set to the current time. Okay, I hope it makes sense to you.
Yes.
Okay.
Sandeep, here one question. If the seed is fixed for the top level of the file, then every random value is the set based on the seed's value, right? But
Yeah.
if some place I need the random value, then how to use that?
No,
Like the
you
one.
continue, right? You continue using random value. How does it matter whether if the seed is fixed or not? Just use your normal thing. It's all random,
Okay.
isn't it? This is all random. It's the seed is fixed. So, and when you don't want it in your program, just change the seed to some other value, and these values will change. Okay, and yeah. So, and then basically, it doesn't make any difference to you. All you want is a random number, it generates random number, just that you know the predictability of it. When you're done with the predictability and everything is working, you can just try doing this, or just try changing the seed to something else and then observe the behavior.
That means the two different machines seed value is same, then the random value is common for the across the two machines at the two system, right?
Usually, yes. Okay. So yeah, that's the power of the right the you want random numbers, but you want them to be reproducible. Every time you run it, they should basically be predictable. Okay. And if you want purposefully another set of random numbers, just change the seed to say something else. That's it. And you get new random numbers. Okay.
Yes.
The main idea is to do the reproduction. This is a big trouble. Like people work very hard and they're just, they're facing this error, or they just figured out that this was working, or this is getting stuck in local minima, how to solve that local minima, basically. And then they forgot to set the seed and they can't get to that local minima again. It keeps on. So that kind of problem happens. So as a good habit, people in machine learning domain, they want to have the seed fixed. Okay. You will see in case of machine learning project, when you are splitting the data randomly, okay, you have train and test data, right? And you want to keep the train and test separate. But what you want to do is every time when you run it, if the test data is different and train data is different, what happens is the model will be different. And when model is different, your accuracy will be different. So no matter, you won't be able to figure out whether you fixed the problem or you have not fixed the problem because data changed or your model changed. And now initialization logic changed, splitting of the data changed, so many things changed. Now you can't figure out whether you solve the problem or not. Because mostly when you're solving a problem, when you're building the model, you would like to slowly experiment with it. Okay, shall I try with different learning rate? Shall I try with different some other value? And so on. So you would like to just have one variable at a time to handle. Otherwise, you can't figure out what's going on. Correct? So that's why you want to fix the randomness, okay? Every time you'll get the same result. All right, moving ahead, yeah. You can plot we have already talked about this one. Okay, now, let's take a look at the salary. We have the salary here. Okay, we'll just say run all above. Okay. Now, we have generated the salary. Okay. Now, let's move on. And here we have plotted it. Okay. Good. Now, notice that the type of salary 0 is float 64. Okay. And if you say x equal to 9, you see the type is integer. Okay. If you say 9 dot, okay, the type of that one is a float. Okay. And yeah. So I hope this is clear. Now, using np.random.rand, you can basically generate, or just random.random, you can generate the data of these many dimensions. Okay, 2, 2, and so on. So now, all right, yeah, I want to show you here that let's say we have a function which is generating 5 random numbers. Okay, every time it's generating 5 random numbers. Now, if you call this function right in the loop like this, okay, every time the answer will be the same. You can see every time we are setting the random seed to 10 and generating this, so you can see it's generating the same values. Okay, now, okay, I hope this makes sense to you. All right, now,
Sandeep, go up a little bit.
Yeah.
This Gen method. Gen method. Yeah. Yeah, this one, Gen 5. Like
Yes.
here is we call the Gen 5 is the 2 times, right? But my output is same. But
Yes.
I want the first one is like the two, both output are different. Then how to generate that here?
Just put the random seed outside, right? Put the random seed outside. That's it.
Okay.
Okay. Because what I'm just trying to demonstrate that if you set the seed and then call this function, then every time this will generate the same result. Okay.
Then what is the use of the random function we are calling? This method seeds we define is the same. Then the value is returning the same
No,
value.
yeah, but you see, this is different from the previous, this is different from the previous, and so on. So it is random, only that the whole chain we have fixed. Whole chain we have fixed. Got it?
Okay. So we can't define the seed as the top level of the file, otherwise the all random value will be the same.
We should define it at the top.
Because
We should always define it at the top. The reason is, what you want to do is, you want the results to be reproducible. It should not be that every time you're running your model and every time you're working out or doing something, you end up getting entirely different results. Okay. So what you want to do is set the random seed, observe if things are going well. If things are going well, just try with some other seed, and then you'll get completely different values, and then you can experiment with those. Okay. So yeah, it's just to make, it's all randomness. It's just that you want to ensure that the things should be reproducible. That's all. Okay. So that's all, because otherwise it'll become you will not be able to debug it. Okay. All right. And yeah, it's the better word somebody said in a previous class. They said deterministic randomness. Okay. This is a deterministic randomness. All right. Okay. All right. One more thing is that you can generate multiple dimensions data. Okay. Say, for example, you want to generate, let's say, so if you want to generate only two numbers, oh, sorry, yeah, two numbers. So this is basically one value, right? This is one dimension data set, right? Then this is two dimension data set, 2 by 2. Then this is 3-dimension data set. You can see the square brackets. Okay. All right. So we can try, say, I'll just try 2 by 3 by 4. Okay, this will look better. So the top level one has how many elements? 2 elements, right? One is this. Okay, so this is 1. And from here to here, this is 2. Correct? So total, this is the total 2 elements. Correct? Inside this element, there are three rows. 1, 2, 3. 1, 2, 3. Right? And inside this one, there are 4 columns. 1, 2, 3, 4. Make sense? Or the other way to think of it, that you have got 3 by 4 matrices 2 times. Good. Everybody okay with the multi-dimensions? Yes?
Yes.
Okay. Now, let's see. I'll just add one more dimension. Now, you got 4 by 5 matrix, 3 times repeated. So this is your 4 by 5 matrix. You see that? This one. 4 rows, 5 columns. How many times? 3 times. 1, 2, and 3. Good. And then this whole thing is repeated twice. Make sense, everyone? Are you getting comfortable with the multi-dimensions, or you are still confused? Yes, no, yes, no. No. Okay.
Getting it somewhere.
What?
I'm saying grabbing, I mean, I'm grasping it up, but yeah, need more practice to grab it fully.
Yeah, yeah, yeah. You won't be able to visualize it, but you'll be able to
Yep.
at least read through it. Okay. Okay. You can't see it with eyes. You can't see it with eyes. You can only
Yep.
see it with the language. You can only express it in the language. Okay.
Yep.
Language sees it. Language sees it. Language or maths. Maths and language are interchangeably used. Okay.
Mhm.
I consider maths to be just language. Okay. So the language sees it, but not the eyes. Okay. Logic sees it, not the eyes. That's the difference.
Yep.
And yeah. So try experimenting with NumPy. And my request to everybody would be to, repeat the gradient descent, the gradient descent we coded earlier. Repeat that using NumPy. You'll be able to do it, everyone. So exercise to everybody is all of this differentiation and everything, try using NumPy. Okay, so define your loss function. So first define generate xy. Okay, generate xy function. It takes number of columns, number of rows, and it generates data. Okay, so do that. And then once you're done with that, define your loss function. Okay, which basically squared loss. It computes the squared loss given, let's say, capital X, actual Y, and what else? Weights. Okay, just call them W. Okay, just do that. And also define a function to right, initialize W. Okay, given. Okay, so this you'll be able to do. And once you're done with it, right? So you have generated, you have written a method for generating data. Okay, this is for generating. In reality, you won't generate data. You will fetch it from some data source. And initializing W squared loss, this is all will be used. And then how would you calculate the loss? Okay, okay, let's call it your model. Okay, it takes right, it takes the value of x and returns y. Okay, so you have the model, which is nothing but, it takes, let's say, weights. Okay, what it does is it returns w times x. Okay, that's about it. Okay, and basically it returns that and then does the np dot sum. Okay, that's about it. And then squared loss is pretty simple. It returns, squared loss is basically calls the model, return model. Okay, and we're passing x and w. This is predicted value. And then, okay, all right, so we'll say diff equals this. This is y actual. And then we are saying return np dot sum. That's it. So this is your squared loss. Good. And then you can define the gradient. Okay, you can define the gradient that given the loss function, this is your loss function, given x and y, determine the gradient. Okay, or am I making mistake? Yes. So given the loss and the weights and the X and the Y, okay, this is your loss function. Okay, this is your loss function. You can essentially call loss function. Loss function takes X, Y, and weights. Okay, this is your old loss. And then you basically increase, and then there it takes the index. Okay, then you basically try increasing that particular loss, and that's about it. So, and basically compute the gradient, then train one step. Okay, do the training of one step. Okay, or you call it update weight. What do you call it? Model.fit. Okay, fit. Yeah. Okay, just write the fit function. Okay, fit function takes everything. It takes X, Y, and of course loss function. It takes what else does it take? It takes initial value of W, and that's about it. And what else? What else does it take? Okay. All right. So using this simple methods, like one step at a time, these methods will be like 2 lines, 3 lines each, and you should be able to do this. Okay. And once you are done with this, okay, you will say train, right? It takes X and Y value initially, then you'll say W equals initialize W. Okay. And then once you're done with initializing W, then what will you do is you will call the fit, and then you'll basically run in a loop. Okay. That's it. Okay. So you can define your own gradient descent. All right, everyone. So explore NumPy, go through the class notes as well, and we will talk about NumPy in more details in the next week. Okay. In the meantime, try to code up things in gradient descent using NumPy, whatever we have done so far.
Yeah.
All right. You'll see that it's pretty easy. And we can actually just code it in like half an hour, or maybe say 15 minutes using NumPy. Pretty simple. And basically you don't have to write too many for loops or anything. Okay. And the code will look much more neater. Okay. So we'll continue from here tomorrow at the same time. Bye.
Okay. Thanks.
Thank you, sir.
Thank you.
Thanks, Sandeep.
Thank you.